Alright, so in this video I want to talk to you a little bit about intermolecular forces and how to predict which type are present between two molecules when they are interacting with each other. Now, in order to do that, I want to go through a little bit with you about the different types of intermolecular forces you can possibly have. And we'll start off up here, dispersion forces, also known as van der Waals forces. These are by far the weakest type of intermolecular forces. They're present between nonpolar molecules that don't really have any other sort of interactions. And really all they are is just temporary disruptions of electron clouds. You know, for example, just imagine these two dots are atoms, nonpolar molecules or atoms or whatever, and here are electron clouds. Well, you know electrons are negatively charged, so when I bring this set of electrons in this cloud closer to this one, it's going to push some of these electrons away. And so you'll get more electrons on the right hand side than on the left, and so that'll build up a very small, and I do mean very small, charge separation. You'll have the same thing here, and this will generate a very small attraction between the two. That's dispersion forces. Very, very weak. Somewhat stronger than that are dipole-dipole forces. Dipole implies the molecules have dipoles, so it needs two polar molecules, those with two polar bonds, to have dipoles. And really all dipole-dipole is the interaction of the opposite ends of each dipole. Hydrogen bonding is a particular type of dipole-dipole interaction. It's got a few requirements that normal dipole-dipole doesn't. First off, you need small, highly charged elements involved, usually nitrogen, oxygen, and fluorine. But on top of that, you also need hydrogen, so you need one of those three plus hydrogen directly connected to that atom. Alright? It's not enough just to have hydrogen present, it's got to be directly connected to either fluorine, oxygen, or nitrogen. As long as one of your two molecules has that present and the other molecule has one of these three, then you'll be fine for hydrogen bonding. Now, ion dipole is somewhat self-explanatory. If you have an ion and you have a polar molecule with a dipole, the charge on the ion will interact with the opposite charge on the dipole. Okay. Now, the word induced here in these last two is pretty self-explanatory too. If you've heard the word induced before, it means causing to happen something that wasn't there before. So induced dipole means a dipole is induced from something that had no dipole to begin with. Kind of like what's going on up here, sort of, but in a much stronger sense. If you have an ion that comes along, let's say we have an ion, let's do Cl minus. There's that ion, alright? And here is a nonpolar molecule. Because remember, induced means there was no dipole there to begin with, so we're going to induce one. When this chlorine comes along, there's a negative charge and it's going to push these electrons over to this side and generate that charge difference again. Now this is going to be a larger charge difference than up here because this is a whole negative charge here. But anyway, what that's doing is generating a dipole that was not there before. So for ion-induced dipole, you've got to have at least one molecule that's nonpolar. And the same thing for dipole-induced dipole, except here the ion induces the dipole, here the dipole does that. So if we have, let's say, something like formaldehyde, for example, alright, with these electrons here, and that negative charge as a result of that, because of that dipole, alright, and then we draw another nonpolar atom or molecule or whatever, and bring that over here, that's going to do exactly the same thing and set up that charge difference. Okay. So again, for these last two, for ion-induced dipole and dipole-induced dipole, you've got to have something that has no dipole there to begin with. You've also got to have an ion present if it's ion-induced, a dipole present if it's dipole-induced. So to figure out what you have between two molecules, there's just some things you want to make sure that you do. Just a couple of steps to go through. And the first thing I would do is look at the two molecules involved and say, okay, do I have any ions present? Because if you don't, the answer can't be any of these two. Okay. Then ask yourself, well, do I have any of these three atoms with hydrogen directly connected to it? Because if I don't, I can't have any hydrogen bonding. When you come down to this one, do I have any molecules that are nonpolar? Because if you do, you have one nonpolar and one polar, then you're going to have dipole-induced dipole. If you have two polar molecules, you'll have dipole-dipole unless you've got any possibility of hydrogen bonding. And if you've got nonpolar molecules both, then it's going to be dispersion forces. So, rather than me just yakking on, let's do an example. Alright? What if I was to say, here are a couple of molecules, CH3, OH, an alcohol, and CH3, CO, CH3. I'm going to put the electrons on here. I don't know whether they're absolutely necessary for what we're doing, but we're going to put them on anyway. Sometimes it helps to actually draw out some of the bonds so you can see that they're there. Here the OH bond isn't shown, so I'm just going to show it. I'm going to say CH3, OH. So we're just going to follow the thinking that we were talking about before. Do we have any ions present? No. Alcohol, this is acetone, is something called a ketone, but you can see there's no charges anywhere. So there's no ions present. So ion dipole and induced dipole can't be possibilities. Look at this guy. Do we have any polar bonds in this molecule? Well, carbon-oxygen is a polar bond with the dipole pointing towards oxygen. We have a dipole here as well. In fact, this isn't the correct geometry because of these electrons. This is actually a bend. But the fact is there are dipoles here. These don't cancel out. This is a polar molecule. And I got dipole up here as well. Okay, so I have what looks to be two polar molecules, which would suggest dipole-dipole. But there's one other thing we have to look at. Notice we also have that OH bond. Alright, so what we need for this hydrogen bonding to occur, we need one molecule with the hydrogen directly connected to the oxygen, nitrogen or fluorine. And then for the other molecule we just need something preferably small and highly charged like oxygen. And what happens is, when I draw that acetone out down here again, okay, we've got our CH3 here again. I apologize for this being kind of messy. And I put these electrons on. Alright. Then the negative charge here is going to interact with the positive charge on that hydrogen, which is generated by the electronegativity of that oxygen. And so what we can show, and this is what we usually show for a hydrogen bond, a dotted line like so. That is a hydrogen bond, only because of this hydrogen atom connected to that oxygen. Alright, so the strongest type of intermolecular force is here, hydrogen bonding. Alright, let's do another one. Let's do Br2 and CH4. So once again we want to ask ourselves, what do we have? Are there any ions there? Hopefully you can say no ions, so it can't be those. Do I have any hydrogens directly connected to oxygen, nitrogen or fluorine? Well, the answer is no, so I can't have any hydrogen bonding. Do I have polar molecules? Alright, well let's look at bromine. Bromine is Br. Okay, if we draw out the structure of methane, from what you've seen before, you will no doubt remember that the bond between carbon and hydrogen is weak enough, or is, I should say, the electronegativities of these two atoms are so similar, these bonds are considered nonpolar. Now what about the bond between two elements of exactly the same electronegativity? Well, of course that difference is zero, meaning nonpolar as well. So what I have is two nonpolar molecules. Okay? And so when we think about that, we said we had two nonpolar molecules with nonpolar bonds. There's only one option, and that's dispersion forces. Alright? So that's what I have here. The strongest attractive force between these molecules is dispersion forces, or van der Waals, as we said before. Okay, let's do another one. NaCl, table salt, and CH4. Let's do CH4 again. I'm just going to write out the Lewis structure of CH4 once again. And I want us to see what we know about NaCl. What sort of compound is that? Well, you know it dissolves in water. Sodium's a metal, chlorine's a non-metal, so that should tell you this is ionic. So it's ionic, that means it's made up of ions. meaning not NaCl necessarily, but Na plus and Cl minus. Most importantly, meaning that I have ions present. Doesn't matter whether it's positive or negative, I mean you'll always have both, but the fact is you have ions present, which automatically says I have narrowed my choices down to only 2 out of the 6. Ion dipole or ion induced dipole. So the only question we have to ask is, do we have to induce a dipole here, or is it already present? Now remember what we said here, non-polar here, so non-polar here as well. If it's non-polar, it means there is no dipole, which means the dipole is going to have to be induced. So therefore the name here would be ion induced dipole. Okay, hopefully this makes sense. And let's just do one more. We're going to do NaCl again, so right off the bat I can say Na plus and Cl minus, but in this case we're going to do this. I'm going to draw the molecule that we had before. We have our acetone again. I'm just drawing this slightly differently than I showed you before, because here carbon is directly bound to carbon. It's a little difficult to see the way I have it written. The way I have it written here, it's much easier to see. Carbon, carbon with 3 hydrogens, carbon with this, carbon with 3 hydrogens again. So we saw before that there is a dipole in this molecule, and that dipole is between the carbon and the oxygen. Alright, just like so. So what that means is my plus charge here can interact with my negative charge here, my negative charge can interact with my plus charge here. Now this dipole is already present, the ions are already present, so once again I have a choice of these two. The dipole is already there, so there's no need to induce it. Therefore the strongest interaction here is ion dipole. Okay, so let's talk a little bit about relative strengths of these things before we go on. The weakest is definitely the dispersion forces, okay? And very close to that is dipole-induced dipole, okay? Because one of them doesn't have a dipole in it. Then there is another one, which is ion-induced dipole, slightly stronger. Out of all the rest though, dipole-dipole comes after dispersion forces, then hydrogen bonding, and the strongest is ion dipole. So hopefully this is going to make your lives a little bit easier, and this stuff is not too bad. Alright, best of luck, thank you.